Thank you, everybody, for sticking around for the last session. This is my first PyData event. I'm really happy to be here. It's been a great conference so far, and I will try to keep it that way. All right, so let's make sure you're in the right place. Let's start off as real engineers. Let's define an objective and constraints. So what we want to do in this talk is build an online interactive data application. Now, in software, there are a million ways to do that. So let's apply our constraints and focus our approach a little bit. So this is a Python conference. So we want to do this in Python. We won't be using R or anything else. And we want this to be zero cost. And that means zero cost for personal use and zero cost for enterprise use. So now we can start making decisions about what kind of technologies we would like to use. So because we want to build something that's online and interactive, we need JavaScript. But we don't need to decide on the JavaScript library right away. The first decision we need to make is actually what Python library we want to use. The reason is because all of these Python libraries that you see here are actually bindings around JavaScript libraries. So once we choose the Python library, we just get whatever JavaScript library comes with that. So for this talk, as indicated in the title, we are going to be using Python bokeh. I'll tell you reasons why I like to use Python bokeh later in the talk, but for now, let's just go with it. Once we choose Python bokeh, that means we'll be using the bokeh JavaScript library. What Python bokeh gives us is just a data application. Once we have that data application, we need a platform on which to deploy it. So we need to decide on some kind of deployment later. And because one of our constraints is zero cost for enterprise use, we're just going to use a Linux server. We're not going to use platform as a service or anything where you might have to pay later on. All right. So this is a dense talk at times. You don't have to remember all the details. I have a personal website, rbtechblog.com. There's a blog post where you can read about exactly what I'm talking about here. So sit back and enjoy. So why Python bokeh? For me, after I saw that the Python bokeh development team had reproduced the Gapminder visualization. Gapminder is a relatively famous interactive data visualization. If you search for it, you'll find a TED Talk. I encourage everybody to watch that TED Talk. Essentially, what it is, it attempts to communicate the statistics of how different countries develop in time. So I don't think you can read the axes, but what we have are metrics that quantify more or less the development of countries, children per woman, and life expectancy in years. And every data point, the size of the circle, is proportional to the population of the country, and the color of the circle encodes what region of the world it's in. Now I'm going to play this for you. This is just me interacting with it in my browser. I just recorded a video of it. So there's China, there's India, there's Taiwan. Once we get farther to the left, and sorry, the year is just not showing up here. There's supposed to be a year that says 1964 right here. So I'm going to press play, and I don't think you see this, but you should see the year incrementing right here, 1988, 1990, 1995, 2000. Sorry you don't see that, but, oh, you do? Oh, there. Okay, it's actually much bigger right here, but yeah, you guys don't see that. So what you can see is how countries develop in time, and it's really great to see that. I encourage you to Google this and watch the rest of that presentation. Now, if you do go to the original presentation, you'll see that they use some very specialized software to create this, something that was developed clearly just for this purpose. But Python bokeh, with the normal Python bokeh package, reproduced this, and I thought that was really great, and that convinced me that I should be using Python bokeh for my own work. Okay, so a more formal explanation why Python bokeh. It was built for web browsers. If you ever decide to use Python bokeh, you'll notice that right away. Everything just pops up right in the web browser. I've been using it for about 2 years, and I haven't been restricted at all. Everything that I can imagine that I want to visualize that's useful in a scientific and engineering context, I can create that with Python bokeh. It's got a nice API. I'll show you some code later, and we'll kind of see what's nice about the API. Okay, at this point in the talk, I would like to tell you about how I use interactive data applications at my company, but in order for that to make sense, you, the audience, kind of needs to know what my company does. So we're going to have a fun little diversion. I'm going to tell you what I do and how data science is involved, and if I've been successful, then you, the audience, should have a better idea of how computer chips are manufactured. Okay, so I work for Cymer. Cymer builds lasers. We don't build the lasers that mount on the heads of sharks, unfortunately. I wish we did. This is the laser that we build. That's what it looks like. It's about as tall as I am. The width is 2/3 the length of the average shark. So let's compare the Cymer laser to my laser pointer, this one. My laser pointer is a very dumb laser. I push a button, it either works or it doesn't work. It looks like green light, but you don't know exactly what shade of green light. You don't know what intensity of green light. You have no control over the green light. It's a very dumb laser. The Cymer laser, on the other hand, is a really intelligent laser, a really smart laser. So the output, instead of constant light, it's light pulses, and you can get up to 6,000 pulses per second if that's what you want. And each pulse of light is exactly what the user asks for. So before the pulse is fired, the user has some interface where they can ask for a specific wavelength, a specific energy, and then the laser delivers exactly that pulse of light. And before the pulse of light exits the system, it's measured, so the user knows what they asked for and what they get, unlike my laser pointer. The way that works is we have onboard sensors everywhere in this system. We have onboard computers everywhere in the system. And we have onboard actuators everywhere in this system. It's actually more computer than laser, this system. And really, most importantly, we have a relatively large team of control engineers that write very advanced feedback control algorithms to make all this work. And we have an embedded software team and kind of all the engineering teams that you would expect. So for the most part, this works all day, every day. It delivers the light meeting the specifications that our customers care about. And this is a remarkable achievement for a laser system. In addition to the light output, all of these onboard sensors output data, a lot of data, and that's good news for a data scientist. If you're interested in purchasing a laser for your living room or patio or wherever, this is the approximate cost. 1.5 million. Cymer was sold in 2013 for that number right there. We were sold to a company called ASML. Cymer and ASML are both in the semiconductor lithography industry. That means manufacturing computer chips. So I'm going to show you a video of the ASML machine. This is the machine that the Cymer laser attaches to. This machine is much bigger than the Cymer laser and way more expensive. So the blue flashing light that you see in there, that's the light from the Cymer laser. It's going through some optics, and it's going through this metal cheese grater thing. That's called the mask. That contains the pattern that is printed onto silicon wafers. There's a silicon wafer. It just finished being printed. It's exiting the system. It's going to be sliced and packaged into computer chips that go into phones and computers and watches and all the other electronic devices. Here's another wafer. It just entered the system. The first thing you need to do is measure the surface of the wafer exactly, because when you are doing photolithography, dimensions of nanometers are critical. Here's another wafer. It's just exiting the system. The wafer whose surface was just measured is now under this projection lens. That's a very expensive component as well. So we'll zoom out, and we'll see the mask again, and so on and so forth. All right, data science is pretty challenging in this environment. Number one, we just have a lot of data to work with. So the Cymer laser outputs thousands of time series signals. There are thousands of events that can happen on a laser, where each event has its own custom set of data. There's lots of unstructured service data, manufacturing data, and we just have thousands of systems all over the world. All models are useful. All models are wrong, but some are useful. So the price of being wrong in this industry is very high. Semiconductor lithography is one of those industries where downtime is measured in some crazy number, like millions of dollars per hour. So we can't build models that are wrong. And I hope you took away from that video that this process is very orchestrated and complex. So there's no time for algorithms in the cloud or anything like that. Everything has to be fast and embedded and automated. All right, now that you know a little bit about the industry, I'm going to play for you a Python bokeh application running on a Linux server that I created to be used within this company. So I mentioned that the laser outputs thousands of time series signals. So depending on the problem that you have, you're not going to want to look at thousands of time series signals. You just want to look at the handful that are relevant to your problem. So I built this application. What you do is you choose from the drop-down menus what it is that you want to look at. Of course, we have to train the people using this to understand if you have problem A, you look at signals A, B, and C, and so on and so forth. So, and then you can zoom, you can pan, you can do all the kind of interactive tricks you would expect to do. Here we're looking at 3 signals that might be relevant to some problem. In case it's not, we can use these buttons to remove figures and add figures and just kind of get the right data in front of our faces that helps us solve some specific problem. All right, so enough about lasers. Professor Alberto Cairo talked to us on Wednesday at 1:15 p.m. about charts. And he mentioned that a picture is not worth 1,000 words, or a chart is not worth 1,000 words. It's only worth the amount of words that are supported by information in the chart. So here's a chart. This is from the Washington Post. Basically what it's saying is that 2018 was a volatile year for stocks, but if you took out all of your money in October, it was a good year for you. Otherwise, it was a bad year. So there's nothing wrong with that. I think Professor Cairo would think this is a good chart because it just says the words that is supported by information in the charts and nothing more. But could we use Python bokeh to make this a little bit more informative, right? The answer is yes, we can. This is another interactive data visualization from my tech blog. And what we're doing here is we have a list of stocks on the left, and we're kind of scanning our cursor along those, and then right underneath you see the time series history of each of those stocks. More importantly, though, we have this colorful chart at the top, and this chart, what I'm doing in that chart is normalizing the price of every stock to a value of 1 on January 1st, and then we can kind of see throughout the year for a large collection of stocks, what is the stock market doing for these stocks? So if we go back to the Washington Post visualization, what they're doing is aggregating by a collection of stocks everything, and we're losing all that information about what individual stocks are doing. But if we have a tool like interactive data visualization, we can get that information back in roughly the same amount of space. So the answer is yes. Python bokeh on Linux server, which was how this was developed, increases the information density by, in this case, enabling multi-dimensional data exploration without excessive aggregation. All right, so I think I've covered a lot. Let's have a little recap. I hope everybody knows why we're here. I hope you know a little bit about how computer chips are manufactured. I hope I've given you enough examples of Python bokeh running on Linux server to convince you that it's something that you might want to do for your own work. Okay, so now let's finally dig in and talk about how to actually build something like this. So no more kind of fancy interactive data applications. From here on out, we're going to work with this very simple interactive data application just to use it as something baseline that we can build and we can understand. And then you can extend it after that. So there's really 3 steps to building something like this. Step 1, we need to build the Python bokeh application and test it locally. So let's just make sure it works on our own computer. After that, we need to put it on the internet. So we need some platform for that. So step 2 is go out and get a Linux cloud server. And then there's 2 things you can do for step 3. If there's just a handful of people in the world that want to see it, if you're not really worried about server security or robustness, you can actually deploy it online very quickly. So I'm going to cover that approach. But if you have a lot of people that want to look at it and you're a little more worried about security and robustness, there's another approach we can take, and we're going to cover that as well. All right, so let's look at the Python bokeh API a little bit. And what I would like for you to focus on is what is graphics code, what is layout code, boilerplate code, and deployment code. One of the nice things about bokeh is there's actually not a whole lot of boilerplate code, especially if you compare it to, let's say PyQt, for example. There's a ton of boilerplate if you're making a PyQt application. So let's look at layout code. Layout code, you see that in line 20. So here we are saying that the layout we want is a column layout where the button is on top of the figure. So that's what's actually creating the layout. Notice that before line 20, we've said nothing about layout. We've said that let there exist a figure object. That's what we say in line 8, but we don't say where in the application should the figure object live. Line 17, we say let there exist a button object, but nothing about where the button object should live. And then finally, once we get to line 20, we said let's make a column layout. So this is nice because if we want to change something about the figure, the code to make the figure is isolated from everything else. If we want to change something about the layout, it's isolated. So when you're building larger applications, this becomes really important that the major components of the application are compartmentalized so you can change things independently. The deployment code is running in the terminal. So I think I left this detail out. This is the Python module that represents the bokeh application. What we do is we open a terminal, we go to the directory where that Python module lives, and we say bokeh serve button.py -- show, and then we get the same visualization that we had before, except it's running in localhost at port 5006. So let's move on. All right, so we have the bokeh application running locally. So we want to get it on the internet as quickly as possible. Forget about security and robustness. We just want it online so we can start sharing it with some people. So what's the fastest way to do that? The first thing that we need is a cloud server. Now, in principle, we could use our own computer and expose that to the internet, but it's 2019, so let's use an infrastructure as a service provider. A really nice provider is DigitalOcean. For $5 a month, we can get a cloud server. The important thing that you need to remember about the cloud server is it's defined by an IP address. And after we get the cloud server, we need to upload our Python module to that cloud server. The next thing we do, and I'm going to assume that the audience knows how to do this, install Python, install bokeh. I think that's a good assumption after talking with everybody here. All right, and then after we have Python and bokeh installed, we log into our cloud server and we run bokeh serve button.py, and instead of -- show, we say -- allow WebSocket origin, and this tells the bokeh server that people going to this IP address and this port should be allowed to see this application. All right, and that does it. That's it. That's all you need to do to deploy a bokeh application online. At that point, you could send to your buddies the IP address and the port number, and they could look at what you've built. This is great. This works, but it's not very secure, and it's not very robust. But like I said, if you just have a handful of people that you're working with, this might be OK. So this is what the fast approach gives you. It's bad because you have an unsecured cloud server. Alberto Cairo would not approve because all we've given the user is the data application. We've provided no words to describe the meaning of it. So we really need to embed it in some web page and write about it, right? Provide the words that are supported by the information and the visualization. The bokeh server was not meant for production. That's a problem. So what we're going to do is I'm going to tell you about a robust approach to doing the same thing where we fix all of those problems. This is what we're going to end up with at the end of the day. All right, so let me outline that robust approach. What we want to do is, again, start with a cloud server. We'll use DigitalOcean. And I'm not going to tell you how to secure a cloud server. I will just tell you to search for DigitalOcean server setup. They publish a tutorial. It's very nice, supported, updated. They have a drop-down menu depending on what version of Linux you have selected. And there's lots of comments and questions. So they can do a much better job telling you how to do this than I can. The next step is create a template Flask application. Again, just search DigitalOcean Flask Nginx. You'll find the online tutorial. It's supported. I asked a question there. It was answered almost immediately. They can do a much better job than I can do. What I'm going to tell you how to do and what is outlined, again, in the tech blog are the steps thereafter. So how do we extend the Flask application with an embedded bokeh application? And there's really 3 steps. We're going to cover each of those. This is kind of where we get into server configuration. So just stay with me. Okay, the first thing we need to do is automate the bokeh server. So if the Linux server reboots for whatever reason, everything just starts up automatically, and the bokeh server kind of runs in the background. This is the proper way to do it. So we are going to use the systemd Linux service utility. The instructions for doing that are actually in the DigitalOcean tutorials that I just referenced. So if you complete those, you'll understand this configuration file much better. Notice that we have a lot of the same elements that we have when we use the very fast approach. The fast approach said bokeh serve, button.py, this option. So we have all those same things in this file. There's bokeh serve, there's button.py, here's our IP address. I'm using a different port because we're using just a different approach. So now I'm using port 5100. I'm putting the application at the relative path /bokeh, and the application name is button.py. Keep in mind those 3 things because they have to remain consistent after this. The next thing that we do is embed the bokeh application in the Flask application. This is a very basic Flask application file. There's a lot of bad coding practices going on here, but don't hold that against me. The bokeh API gives you a function, bokeh.embed.serverDocument, which does exactly what we want to do here. It allows you to embed a bokeh server document inside of a Flask application. The output of that function is an HTML tag object. The input is just the location of the application, bokeh, in our case, /bokeh/button, which is consistent with our last bit of server configuration. The way you send this tag to your HTML file is like you see here. You don't have to remember that. Just go to rbtechblog.com. The final piece to this puzzle is we need to put the bokeh server behind a reverse proxy so that we are not using the bokeh server in production. If you follow the DigitalOcean tutorials, they talk a lot about Nginx and how it's used for this approach. After going through those tutorials, you'll recognize this configuration file. We have to extend that by adding a new location block. And that new location block has to be consistent with everything that we've defined up to this point. It is. Here's your port, 5100. Here is your bokeh server location, /bokeh. If you like more information, or if you want to use something else like Apache for your reverse proxy, search running a bokeh server, and the bokeh team has created some documentation about that. So that's it. You do that, and you have a robust deployment on a Linux server of a bokeh application embedded in Flask. So I know this is very simple, but you can imagine how we could build something more complicated here, more useful, and then we would describe it in Flask, just like we would build any other web page. So that's it. Quiz for you guys. Let's see if you can get this. If I navigated to the IP address of the cloud server /bokeh, what would it show me? Is that what you were pointing to? Yeah, exactly. Yeah, it just gives you the bokeh application at that point because that's where we asked the bokeh application to live. Very good. All right, thank you, and I'll take any questions.
Any questions?
Yes.
Hey, earlier we had a talk by the Plotly team. Excuse me. I was just wondering if you'd use that at all.
No. I found bokeh first, I liked it, and I stayed with it. Yeah, I've seen other people use Plotly, and I heard about Dash today. So those also look useful.
Does the Python bokeh server handle all of the sub-selection? If you had a billion-point time series record, does it intelligently stride through the data to plot it?
By default, no, it doesn't. But the bokeh team recognized that, and they built an extension which I have not used. It's called Data Shader. You can search like bokeh data shader, and there's PyData talks about that, given by an actual member of the bokeh team, which I'm not, and it looks very impressive. Yes?
For the actual sensor data, did you end up streaming that data in? And if so, what technologies did you use for that?
No, that the way that system works is the laser's running in the field, it's collecting data, and then every so often it sends it back to San Diego. It goes into a database, and then the application reads from that database. Bokeh does support streaming data. This is so again, I'm not a representative of bokeh. You could probably find a presentation about bokeh streaming. I know it's advertised on the main page of bokeh, bokeh.pydata.org, that it supports large and streaming data sets. So I trust that it does, but I haven't used it.
I want to thank you for exposing this. I've never seen this. It's going to solve a problem for me, so thank you.
Thank you.
I did a quick search on the web. This does work in Jupyter Notebooks. Have you had any experience of that, yay or nay? I mean, it's good or bad, I should say.
No, I haven't. I've seen it done in Jupyter Notebooks. The people that are looking at the applications I build don't want to have anything to do with Python or Jupyter. They just want to go to a web page and see what they need to see. It's actually going to be easier for you to build something that works in Jupyter because it's more tightly integrated. You can avoid a lot of the server configuration that I talked about.
Any more questions? Okay, thanks again.
Thank you.